So last class we were talking about gases. Today we're going to wrap up chapter 9, and we're going to do so first by thinking about our collaborative problem-solving strategy of TAPS, or think paired problem solving. So I want you to think about your role as the listener and your role as the problem solver. If you're the listener, you're really trying to be attentive to the steps or the sequence that's used to solve a problem. If you're the problem solver, you're really being attentive to what's the information or the clues that are given in the problem that help you to determine that sequence. So one of the best ways, I think, to figure out what you need to do in terms of a problem is to think about the information that you're given, maybe to organize that. So one of the ways you can organize that is by listing the variables that you're given in the problem. So in this case, I'm given a volume. I know it's volume because of this unit liters. I'm given a temperature because of the unit degrees Celsius. And I'm given pressure. I know that because of the unit kPa and the fact that I'm told that it's pressure. But I also know that I need to convert kilopascals to a unit that I'm more familiar with, so I'm going to convert that to atmospheres. So I have this information. I'm going to notice that the only thing that I don't have, based on my ideal gas law equation, is moles. And so I know I have this expression for moles, which is PV is equal to nRT. And, if I'm interested, I can always rearrange that to solve for moles. So N is equal to PV over RT. Now, if I solve this expression, I'm going to solve it, and I'm going to figure out that I have 0.041 moles of gas. And so this is going to be true regardless of whether or not it's methane, which is in flask A, or carbon dioxide, which is flask B, or ammonia, which is flask C. So this is a great example of the type of problem that you're going to be solving on Wednesday's quiz. Our scientist spotlight today I'm really excited about. So Deirdre Sullivan is an instructor at Monterey Peninsula College. So she has 2 degrees in aquatic biology and in geology. She's also in the Women Divers Hall of Fame. And most importantly, she's the director of MATE, which is the Marine Advanced Technology Center. And she's really responsible for developing a marine remote sensing in our area. And so what's really cool about that is that because of the MATE Technology Center, lots of folks are learning how to build ROV, or remote operated vehicles. And one of the ways those can be used is to map the Monterey Canyon. So if you take a look at this image, Monterey Bay is the land, but then there's this beautiful canyon that we can't see because it's covered by water in the ocean. In fact, there are aspects of the Monterey Canyon that are as deep, if not deeper, than the Grand Canyon. So Deirdre Sullivan is our scientist spotlight for today. She's a really great example of someone who broke barriers, both as a diver and as a research scientist. Our focus today is going to be on constructing explanations and designing solutions. And we're going to tackle the remainder of our learning outcomes. So we're going to create and use appropriate equations relating 2 sets of conditions for a gas. We're going to learn about how to solve for partial pressures of gases. We're going to calculate the mole fraction of gases in a mixture, and then we're going to use mole fractions to find partial pressures. And then we're going to think about how to use stoichiometry in combination with PV equals nRT. As a reminder, you were given in class an equation sheet. And what's really important about that equation sheet is that you recognize that you're going to have access to the equation. So for example, you'll always have access to the equation PV equals nRT, but that's not really the most important part. The most important part is that you know how to interpret that equation. So you know that P stands for pressure, that V stands for volume. We want to make sure we're using liters. That N stands for the number of moles, that R is the gas constant. And here, you're going to have some choice, and you have to make sure that you choose the correct gas law constant. And then T is temperature, and we always want to use Kelvin. The reason why that's super important is because you're going to have several different units you can choose from, and you want to be able to match your units to the type of equation that you're solving. So here's a really great example. A rail tanker car with a volume of 130,000 liters is sealed at a temperature of 100 degrees Celsius. what should its volume be at 10 degrees Celsius? So PV equals nRT, we're going to solve for the gas constant R. We solve for R because it's a constant. And so if it's a constant, that means it's not going to change. R is always going to be the same. So that means that we can say one set of conditions, P1, V1, N1, T1, has to be equal to the gas law constant. So we can also say that gas law constant is equal to a different set of conditions, P2, V2 over N2, T2. Because both of those are equal to R, we can set them equal to each other, and that allows us to then simplify and solve. In this problem, we're not given pressure, and we're not given moles, so we can assume that those are constant. Because we cancel those out, our equation then simplifies to V1 divided by T1 equal to V2 divided by T2. And in this case, because of the information we're given in the problem, we want to solve for V2. And once we've that went really fast. Once we've rearranged and solved for V2, then we're just going to substitute. So in this case, we're substituting in our V1 and T1 as well as our T2. And again, we want to make sure that our temperature is in Kelvin. When we do that, our kelvins cancel. And so we're left with liters, which is good because that's the unit that we're looking for. Probably most critical for this problem is that we pay attention to the fact that we can only have 2 sig figs. So that means that our 98,645 liters, we need to round up to 99,000 liters. So what's the big idea here? Well, the whole point is that we're able to take changing conditions. So if we're given one set of conditions, we can find a variable in a different set of conditions. Well, that's really important because we can start all changing conditions gas law problems from this place. So that means that as long as we know what R, the gas law constant, is, we can solve for any set of changing conditions or changing variables. For a problem like this, it's particularly important that I go through and I identify the information in the problem, what I'm being asked to solve for. Now, this might be a step that you're tempted to skip, but will actually make it easier for you in the long run. So notice when we rearrange and solve, we're solving for V2 in this case. You want to do all of that algebraic manipulation before you substitute and solve. You're less likely to make mistakes that way. And then, if you've already identified your variables, it's super easy to then substitute and solve. And notice our units cancel, and our final answer gives us 99,000 liters. Because again, we have those 2 sig figs. The other aspect of gas laws we're going to take a look at today is Dalton's law of partial pressures. Dalton's law says that the pressure exerted by an individual gas in a mixture is known as its partial pressure. So assuming that we have a mixture of ideal gases, we can use the ideal gas law to then solve problems involving gases in a mixture. So Dalton's law of partial pressures states that the total pressure of a mixture of gases is equal to the sum of the partial pressures of the component gases. So for example, if I had 159 millimeters of mercury of oxygen, and I had 593 millimeters of mercury of nitrogen, when I combine those two together, I'm just going to add the 2 pressures. So 159 plus 593 gives me 725 millimeters of mercury. So Dalton's law of partial pressure means that if we in order to find the partial pressure of a component gas A stands for anything, in a mixture of gases equal to the mole fraction multiplied by the total pressure. So P, the partial pressure of anything, is going to be equal to the mole fraction A times the total pressure. Now you might be wondering what mole fraction is. Well, mole fraction is simply the number of moles of anything divided by the total number of moles. So let's look at an example. Heliox is a mixture of oxygen and helium gas used in deep sea diving and in medicine. If a heliox mixture is 68% oxygen and 32% helium by mass, what then is the mole fraction of oxygen in the mixture? So we assume that we have 100 grams, so that means we're going to have 68 grams of oxygen and 32 grams of helium. When we convert that to moles, our 68 grams of oxygen will be divided by the molar mass of oxygen, so that's 16 times 2, or 32 grams of oxygen, that's going to give us 2.125 moles of oxygen. And if we had 32 grams of helium and divide by the molar mass of helium, which is 4.003 grams from our periodic table, then we have 7.994 moles of helium. So we need to find the total number of moles. We're going to add those two values together. So 2.125 moles of oxygen plus 7.994 moles of helium gives us a total number of moles of 10.119. And so to find the mole fraction of O2, it's the number of moles of oxygen divided by the total number of moles. So 2.125 moles of O2 divided by 10.119 total moles, that's going to give us a mole fraction of 0.210. Notice it has no units. It's unitless because the units have canceled. So critically here, there are a couple of steps we want to be attentive to. Calculating the mole fraction means we're going to have to convert anything we're given in grams to moles. Then, in order to find the mole fraction, we have to know the total number of moles. We have to be able to add up all of our moles. And then it's a ratio or a part over the whole. So the part is the number of moles of oxygen. The whole is the total number of moles. So 2.125 divided by the total number of moles gives us a mole fraction of 0.210. We can then use this mole fraction to solve for the partial pressure of oxygen. If we know the mole fraction and we know our total pressure, then we can multiply those two together. So in this case, 0.210 times 1 atmosphere gives us a partial pressure for oxygen of 0.21 atmospheres. And, right, if we say, for example, had a different total pressure, all we would do is change that value, and that would allow us to, again, calculate the partial pressure of oxygen, as shown in the second example. All right, make sure that you stick around for S cubed. It's a chance to familiarize and connect, as well as apply and analyze, and make sure you have the chance to evaluate how you solve problems. As a reminder, we have discussions on Thursday from 8 to 9, 3 to 4, and 4 to 5. And then in your last minutes of class, we want to organize our goals. So for example, a great goal would be to learn the variables and their respective units. We want to incorporate metacognition. This is thinking about our thinking. So do I understand mole fractions? Do you understand how to solve for mole fractions? And then reflect on your learning. How do I convert kilopascals to atmospheres? Next time we'll be taking a look at thermochemistry, chapter 5. Thanks again. Have a great day.